So we saw that if the language is 0 power n, 1 power n, n greater than or equal to 1, then PDA exists. Then 0 power n, 1 power n, 2 power n, when n greater than or equal to 1, we intuitively argued that no PDA exists. The structure of PDA itself limits us to accept languages of this type, because using stack you can only remember one symbol, and the moment you scan 1, the information about 0 is used and it is lost when you finish reading 1, which means when you start reading 2, we have no information about number of zeros and number of ones. Then we saw that something like 0 power n, 1 power n, 2 power m, 3 power m, something like you are expected to remember things in pairs, then PDA exists. But the same thing, if you do it like this, 0 power n, 2 power m, 1 power n, 3 power m. Suppose you go for such a design. Okay, we push capital A for this, then we start pushing capital B for this. I have to use a different symbol, otherwise this index and this index, they may be different, right? So now we see 1, but 1 should be mapped with these two, but it is a stack, so the top portion contains information about 2, not information about 0, which means even this language, it cannot be accepted by PDA. Okay, although these two are grouped in pairs, but the order of appearance also matters when it comes to design. Okay, and then we ask for languages of this type, say L is equal to 0 power n, and where n is a prime number. Okay, so something like this. So which means let's leave 1, 2 and so on. We start with 3 and we want to accept strings of this type. Okay, you want to include 2, then you can start from 2, but let me start from this. So now, can you come up with a PDA which will precisely accept this set? In general, 0 power n, where n is a prime number. Remember, it can scan and somehow remember the number of zeros read through a symbol or set of symbols stored in the stack. But the machine cannot tell you whether it is 3 zeros or 5 zeros or 7 zeros or 11 zeros and so on. So any computation of this type, machine PDA cannot do. So no PDA exists. Consider this language, say 0 power n, such that n equals m square for some integer m. Something like 0 power 4, and 4 is 2 square, and 0 power 9, 9 is 3 square. Okay. So n must be a perfect square. Now when you start reading zeros, right, so the machine can only read zeros and going through a loop, but being in Q0, one cannot tell that number of zeros read is so much. And even if you go through the states, for example, sequence of states, on reading a 0, I go to Q1, on reading another 0, I go to Q2, but number of states is finite in nature. So at some point in time, you have to come back to this place, or somewhere you will have a loop around. Because number of states are finite in nature, then at some point in time, you will come back to some state that you have seen before, or you loop around. Okay? I'm just describing with input symbol, and along with that, you will also write the stack symbol, how stack is modified and all that. But this is enough. This is enough to comment about this language, that this cannot be accepted by a PDA. So larger message, something like a pattern of this type is okay, but a pattern, in addition to that, some computation like n is a prime number, n is a perfect square, things like that, PDA cannot be designed. So what limits the PDA from accepting these languages? And one side, there is a stack. With that you can only do minimal computation, and one cannot write on the tape, and one cannot move left, one can always move exactly one cell right. So all this limits the PDA from accepting languages like this or this or this. So what about its limitations? You see that no left move, no right on the tape. We are writing on the stack, but no write in the input tape. Fine. And you have exactly one stack. Maybe we can increase the computing power if more than one stack is available. What is available is exactly one stack. Now let's try kind of bringing some variation to this mission and see whether some of these limitations can be addressed to some extent. Fine. Let's look at that. So we have PDA. These are all the variations. A variant number 1, what we will do is PDA with, say, 2 stacks. Allow PDA to have 2 stacks, that's 1. Variant number 2, allow left move, PDA along with left move. So variant number 3, allow right operation. Okay. And when you allow right operation, because you can write on the tape itself, we don't need to have additional storage like stack, or let it be there. So let me write with stack or without stack. Now these are all the possible directions in which one can think further to improve this design and see whether its computing power can be increased by giving these additional features. And then again, suppose we provide this feature, you get a new mission, start studying its computing power limitation, and that's how the research progresses. Suppose it's a PDA with 2 stacks. Okay. So there will be an input tape, a read control or a CPU, we will have two stacks S1 and S2. Let's look at this language, the very first language that we discovered that it cannot be accepted by any PDA. So let's take this design and see whether this language is acceptable by this modified automaton or not. What I do when I read zeros, suppose input is 0, 0, 1, 1, 2, 2. For 0, I perform push. Okay. Then when I start reading 1, I do two things. So pop A and push A onto S2. You pop this and place it inside. Okay, it becomes like this. Then you pop this and place it inside. Okay, so because you have an additional stack, you can pop and store it over here. Now what I do, I start reading 2, and for this we pop this and we pop this. Finally we reach Z0, which means number of zeros, number of ones and number of twos are one and the same. For zeros we push so many A's, and number of A's must match number of ones, and otherwise there will be a mismatch. Something will be left out over here, or number of ones will be more. So when we come over here, we know that zeros and ones are one and the same, and we still remember that information using S2. We still know the number of ones read or zeros read using S2, and when we start reading 2, we perform pop, and at the end, if the stack 2 is empty, you conclude the input is of the form this, and you accept the language. So it's interesting to see that the moment you introduce one more stack, we are able to accept this language. Now an interesting question, can I extend this further? For example, 0 power n, 1 power n, 2 power n, 3 power n, 4 power n, where n greater than or equal to 1, and sigma as these input symbols 0, 1, 2 up to 4. Answer is yes. So when you pop this, this would be empty, push it again. When you pop this, this would be empty, push it again. So you can keep track of any number of input symbols as part of the string. And just by introducing one more stack, its computing power has increased tremendously, and from a simple language like 0 power n, 1 power n, to it can accept any string of this form, and one can keep extending this alphabet as well, and you bring say 26 alphabets, and for each of them one can write that rise to the power n. So just by introducing one more stack, its computing power has increased. But can this solve other questions, meaning L is equal to a power n such that n is prime? Answer is no. With this you can only remember a pattern, but no arithmetic can be done. Can this check whether L is equal to a power n such that n is equal to m square for some m? Answer is no. So pattern matching computing power has increased, but this arithmetic, it is still not possible with this modified design. So now supposing I allow write operation and along with read and stack, can we increase its computing power? Or you allow write operation, also allow left movement, and will that increase the computing power? Okay, so all that we shall see next. So we are going to see a mission called Turing mission, which is an extension of PDA. So it starts with FA, then PDA, then we go to Turing mission. So this mission, similar to finite automaton and PDA, wherein the control is read-write control, which means it can read a symbol and it can also perform write when it reads a symbol. So both read and write are possible with the input tape, and read control can move both left and right. So we allow the control to move left as well as right. There is no additional storage, because if you want to write something on the tape itself, one can write. So that's all the mission has got. And with this, let's see what is that the mission can do. Languages like this, that this mission cannot accept, even the modified one, can Turing mission accept? Okay, which we shall see next.